ExCalibBEM is a tool to assist building energy simulation experts in the calibration of their Energy Plus or DO 2.2 models. ExCalibBEM is a simple and complete user interface to GenUp, a generic optimization program developed by the US laboratory LBNL. The tool interface has 4 tabs: Project, Simulation, Optimization, and Visualization. The Project tab allows to define the simulation engine, Energy Plus or DO 2, the input file, the weather and measure data file. The measure data file is a text file. In this example, it represents the total electric consumption of the building on 15-minute intervals. To make sure ExCalibBEM refers to the proper version of the specified simulation program, the configuration menu allows to specify the path where the program is installed on your machine. The Simulation tab simply allows to launch the simulation from the inputs of the Project tab. The sub-tabs show the input data file and also the output files such as the ESO, CSV, and the error file. The Optimization tab includes 5 sub-tabs. This section contains all the information for defining and launching the optimization run. The Definition sub-tab specifies the algorithm types and their related characteristics. All the algorithm types supported by GenUp are included. As you may see, algorithms such as the GPS and PSO can be selected. For this example, the parametric type is selected. The Parameters sub-tab allows to define all the parameters and their characteristics such as the type, discrete, continuous or function, and minimum and maximum values. Also, a very useful checkbox list allows to link each parameter to the one or multiple objects properties of the input file. This functionality allows an automatic generation of the input template file required by GenUp. For example, the parameter minimum outside air system 125 has been created. This parameter has a continuous type, so the range value is from 0.1 to 0.3 cubic meters per second with 2 intervals. This parameter is linked below with the minimum outside air flow rate property of these 4 selected objects. The plug load zone 125 parameter is another example. It is a discrete parameter which values are respectively 5, 10 and 25 watts per square meter. This parameter is linked to the watt per zone flow area property of the 5 selected objects. With this setup, 5 parametric runs will be done according to the variation of these 2 parameters. The Objective Function sub-tab allows to define the location of the objective function, so the value to minimize. It is possible to call a post-process program written in Python after each evaluation to compute the objective function according to the simulation output results and the measured data file. The objective function 1.py file is included in the installation package. It evaluates the coefficient of variation of the root mean square error between the simulated and the measured data at each time step and prints the value in a simple text file. After, the user has to refer to that file, which has an IGO extension, and has to specify a delimiter to tell GenUp where the value is located in the file. If parametric algorithm type is selected, the objective function is not really used by the program, but it should be specified. The GenUp Files subtype allows to generate and visualize all the files required by GenUp. For the input template file, the HTML mode is useful to verify the indicators automatically generated for each parameter. The command file and the initialization file could be also visualized and modified if needed. Finally, the Run subtab allows to launch GenUp and the optimization problem. The graph on the right prints the value of the objective function after each evaluation. So here, as we can see, 5 simulations have been made. The last step is the Visualization tab. it is used to easily plot and synchronize on the same graph the simulated and measured data. For example, we add on the graph the measured data of the total electric demand. We then add the fourth calibration result file, which refers to the 10 watt per square meter for the plug loads. Finally, we can add the fifth calibration result file, which refers to the 25 watt per square meter for the plug loads. So as we can see on the graph, the simulation run period covers only 2 weeks in January. When zooming in, we can clearly see the discrepancy with the measured data. To get a more detailed analysis framework, we can export the data to ExCalibBEM spreadsheet. ExCalibBEM is an Excel template file offering multiple views to analyze data. For example, our series of data have been copied into the Excel file and can be visualized with different frequencies. The slicers at the top can be used to easily filter the plotted information. Other interesting worksheet reports exist, such as contour plot and scatter plot. The statistic worksheet computes the coefficient of variation of the root mean square error and the normalized bias error against a specified measured data in order to qualify our calibrated models. This concludes our brief overview of ExCalibBEM features. For additional information, visit our internet site www.cmeb.ca. Thanks.